Hi, everybody. Today I'll be talking about microservices in a hybrid world. First up, just want to introduce myself. My name is Kyle Davis. I am the head of developer advocacy at Redis Labs. You can find me at these different places, and I've been using Redis for a long time, but more importantly, I've been developing applications and working as an architect and developer for many, many years. And you know, in the past few years, I was introduced to the microservices architecture, and it really fundamentally changed how I see how applications are built. And it really does serve as a great way for many applications to be developed in a fundamentally different way from what they have been in the past. And it's a very approachable format that does lead to a better overall system, in my personal opinion. Now, there is some controversy around microservices. I think microservices are one of the things that are oftentimes attributed to a variety of different ills. I'm going to go over kind of how I see and how the industry sees the microservices architecture, and then how it kind of fits into the hybrid world. So first off, I want to level set a little bit here. Microservice doesn't equal a bunch of small services. And I think this is the most common misconception that people have, that they're going to have, 1,000 services and they're going to be 100 lines a piece and everything's going to be fine. And I think that doesn't really reflect the reality. So what is micro about microservices? Effectively, in a monolith, the responsibility is across the entire application. And that application, everything is tightly coupled together. Now, contrary to what most people think, this doesn't necessarily mean that everything is one binary executable. It can actually have many different executables, but the really thing here is that there's a responsibility that is shared among all those executables for the responsibility of the application. And it really changes how you organize the code. Now, in the microservices architecture, basically what you're doing is dividing out the responsibility of the application into smaller chunks. And that's where the micro comes in. So in a monolith, you're actually organizing your code quite differently. And this is something that I've done in the past, is I organized my code this way when I was building big applications. Basically, you would have the entire application, but you'd have a section, either through that libraries or through modules or through even separate binaries or scripts that are responsible for different technical capabilities of that. So for example, you might have a lot of different code that's kind of responsible for sending emails out in an e-commerce application. Or for example, your REST API might be somewhere else than maybe PDF generation. That is fundamentally different from how the microservices approach works. In the microservices approach, basically what you're doing is you're transposing the organizational units of the overall organization onto the architecture of the application. So in this case, let's think of this of a kind of mythical e-commerce application. And some of the services you might have there is you might have a fulfillment service, you may have an order service, and you may have a user service. And those kind of reflect the organizational view of fulfillment, order, and user, whereas they may have many of those technical capabilities all in the individual services. Now, I want to be pedantic for a moment. You will hear people say, this is my fulfillment microservice. And for people who have studied this and seen how these ideas kind of came about, that may make your skin crawl because the preferred nomenclature is actually a fulfillment service. So the microservices architecture is made up of services. This is something I put in all my presentations about microservices. I'm sure this particular crowd knows this, but it is something that really does make a difference, and I think actually informs how you think about microservices. Let's talk about some more kind of properties of this. Each service has its own centralized or non-centralized storage here. So each service has its own local storage that is available only to that service. So you are reading and writing on the fulfillment service to a single storage place, and that fulfillment service cannot read and write to the order service. Now, there are exceptions, which we'll get to a little bit later, but they're kind of siloed here, and each individual one is responsible for its own storage. Now, the other kind of property we have here is that services are stateless. Now, what do I mean by that? In this case, it means that each individual instance of the service does not keep state on its own. And that's actually kind of important how it works with storage too. So take, for example, the fulfillment service and in a situation where one of the instances dies, right? It can then be brought back up and replaced without having to worry about anything. And this kind of goes to the cattle not pets part of some of the modern thinking around servers and services. But what's really nice about that is that you are always just reattaching to the storage that you might need, the database that you might need. The other thing is that you can actually have many different instances of a given service. And because they are stateless, it doesn't really matter. So instance 7 of the order service is still attached to the same storage as instance 1. So it doesn't matter if instance 1 or instance 7 is responding to any given request. Now, the other thing, shifting gears away from statelessness, is talking about the interface. Now, this is a little bit of an overloaded term, but really this is the interface between different services, what I'm referring to here. Now, traditionally, this has been something that would be like a REST interface that runs over the HTTP protocol or HTTPS protocol. Now, this is not the only solution, which we'll get to a little bit later, but basically, when you're doing this, one service is talking to another over kind of the standardized interface. And the key with the interface is that it is the stable part of any given service. So in that case, let's just say that you have some problems with your order service and the way it was built was not up to snuff. You can entirely replace that as long as you keep the interface, how one service is talking to another, the same. It doesn't matter underlying what you do to it. So you could go in and have something implemented in, say, Node.js and say that this doesn't perform, then you can replace it with something of an entirely different language or change the underlying data stuff. Now, a single operation may involve many different services. Now, I live in Canada, so we're going to use the example of purchasing a hockey stick. In that case, what we're going to be doing is actually looking at how that might work and what actually happens underneath the covers when you purchase the stick. So in this case, you have many different services talking to one another to accomplish the single role. Now, this is where the rubber starts hitting the road when it comes to a hybrid deployment. What happens? Now, these are all synchronous requests from one to the other. What happens when you cross maybe a boundary between public and private cloud? You have your on-prem fulfillment service, and then public cloud is the other two services. This really does have some implications. Now, what you really have to ask yourself when you're doing this and you're setting up an architecture like this is, are these the same? So in a public cloud, you have these two services that are talking to one another, and you have certain guarantees and certain things that you take for granted, certain things that you don't take for granted, and maybe you're working around. Whereas when you cross the public cloud, private cloud boundary, what does that mean? Is there different guarantees there? Is the latency the same? Oftentimes, these are vastly different types of connections. You even have to consider things like security. And are you in the same rack? Maybe that's something that you can have very fine control over, and have a shorter cord physically in an on-prem situation. In a public cloud situation, you may not have that control. Or when you're crossing the boundary, maybe you don't have the same guarantees about stability of those connections. And how does that impact an overall application built in a hybrid world? Now, there is an alternate way of viewing this. Now, we have assumed HTTP up to this point as the communication method and a synchronous communication method at that. Let's start thinking about things in a little different way. Now, we've talked about interface being key and all this stuff in private, databases and things like that. Now, we mentioned earlier about the exception, and let's talk about it now. In this case, you have the database for fulfillment, reading and writing to it. But if you have a situation where you have another service reading from the database of another service. What's the key here? Why is that different than anything else? At that point, that part that you are opening up for other services to read can be considered an interface. And at that, when you have that, you just have to keep it stable like you would, just like your HTTP interface. But you can only read, and read is a non-destructive, any non-destructive activity functionally. And so in this case, if you do want to make changes, you have to go through another synchronous form of doing this or another interface. You can't just write to the other database. That would violate a lot of the principles of the microservices architecture. But what does it really mean? Well, if you were doing this, you did a write over here, why wouldn't that be a good idea? The reason is you start generating very tightly coupled applications. And also there's a risk here if order service makes a change, the fulfillment service isn't expecting, then you have the situation where you might as well put those two services together. Now, I want to talk a little bit more about this, but I want to shift gears for just a moment and talk about Redis. Redis is an in-memory open source database, for those of you who don't know. We are designed for a lot of different use cases, and it's pretty widely known in the industry, but there's people tend to underutilize Redis, and so I go over a lot of this in any presentation I give in front of people. It stands not only for a remote dictionary server, that's a little bit controversial these days. On the 10-year anniversary, Salvatore, the guy who created it, did let it go that basically he was that was a bit of a backronym, and that he is really looking for a 5-letter domain name. So it really did have a little bit of a strange origin to the name. Like I said, it was created by Salvatore Sanfilippo a little over 10 years ago. It's open source BSD license, and I encourage anybody to look at the source code. I think that's where the real proof of any technology is. If you can read the source code and say this is really good code, then you can use it. Now, I work for Redis Labs, and Redis Labs is the home of Redis, but certainly also it provides Redis Enterprise. And Redis Enterprise is an in-memory multi-model database built on top of Redis. But what it's really used for is it provides ways to enhance Redis, of course, but it allows operations of Redis to be a lot simpler for people who use a lot of Redis. So if you're a small organization and you use a ton of Redis, that's fine. Redis Enterprise is for you. Or if you're a large organization and by function of that, you use a lot of Redis, then Redis Enterprise is certainly for you. And if you're frankly building a microservices architecture, probably Redis Enterprise is for you as well. There's very few true small microservices architectures out there, and Redis is usually a key part of most of them. Now, from the data model point of view in Redis, we descend from this whole idea of the key value store, and key value stores have this idea of a key and then some sort of data on the other end of it, and that's about where it ends. Redis has extended that, and basically now you have another layer, which is the data structure layer. The data structure layer kind of informs how the data is stored and retrievable by a given key and commands. Now, I'm not going to talk about all these different data structures, and in fact, you can expand this with modules. But what I am going to talk about today is Redis Streams. Now, Redis Streams is a series of time-ordered entries in a database. We'll get into a little bit more, but you can think of them as field values that have a way of being intrinsically ordered, and it really provides a way for you to go back and look in something in an immutable way. There's other ways you can do this. You can implement this type of data structure on your own. There's other services that do this, but I'll talk about Redis today because this is what I know. Now, let's kind of look at this from a very high level. How does this work? So you have many services asynchronously reading from a given stream. And the way it kind of works is you have your one writer to the stream. In this case, whoops, wrong direction. You have the user writing to the stream, and then you have other services reading from that stream. So we're still using our fulfillment and order service here. So the key thing is that they're keeping track of their kind of last seen. Now, everything in a stream is time ordered, and it has a timestamp and a sequence number that prevents any type of duplication here. But I've kind of reduced this down to minutes for this high-level example. So fulfillment, for example, has a last seen of 9:02. I kind of think of this as like a bookmark almost. So fulfillment knows that they left off, last time they processed something was at 9:02. So they can then read from the stream and say, give me everything or give me a few entries past 902. It will do that. It processes something and then it updates its last scene, and then it will loop back and do it again. Order can have a separate bookmark for it. So in this case, it's 904, and they say, I'm going to wait for something to come along. And when it comes along, I will then process that and update my bookmark. And that's how you do asynchronous communication among different services in the microservices architecture. Now, let's dive a little bit deeper into the data structure itself and how that has some implications on things. So you have a series of different ones. In this case, the way Redis streams works is you have fields and values, and they're kind of ad hoc. You can put anything you want into them. So you can have different fields or different values in them, as long as you're kind of keeping the same commands for a given data structure, in this case streams. These are called entries. So every time you create a new entry at a given stream key. And this is something that you'll see the time sequence is automatically managed by Redis. So diving a little bit deeper onto this, how does it actually work? So you have your stream key. It has some data in it. It's, we have one process which is adding to that. So it's going to add the stream entry, which the field and values that you put into it. It will assign a sequence number and timestamp, and that'll be the stream ID. That stream ID is then returned back to the application, and it can do whatever it needs to do with it. Now, the reading services here will do what's called a request and wait, which will basically using the command xread, which is the Redis command. You don't necessarily need to know that to understand it. But what will happen is it'll take its last known entry ID and then say, give me everything for that. Now, if nothing happens, it's waiting. So in this case, it's kind of a push model. So it's holding it open, saying for a given amount of time, I'm going to wait for anything to come in. So when it does, it'll return data. And that data will include the fields and values that it had, as well as a sequence number. So then what will happen, it'll process that and it'll acknowledge that, which we'll get into in a moment after the processing has occurred. And then it will immediately start saying, my last known ID was the ID from above. So you can see down here in this thing that just came on the screen, this is the last known ID. So as we move forward, we will then process that again and keep on going. Now, if there's a timeout on this, and if nothing happens, it's just going to keep on pushing in that value, and it can wait, let's say, up to a second if you want to put it that way, but you can specify that in a little bit different way as well. So this is actually quite important to understand that as you do this, it creates this loop, and it will never be able to lose data because it's constantly keeping track in its own data storage, the services data storage, where it kind of left off on this. So it actually becomes quite resistant to a lot of failures. Now, let's talk about that in a little more depth. Redis, like I said earlier, is an in-memory database, which has some interesting things as far as durability is concerned. This is where a lot of people kind of raise an eyebrow when you're doing these type of things. But this is something that you'd want to look for in any data storage that's doing this type of workload. So in this case, your service is writing to Redis to a stream. And the command here is xadd. You can see that on the stream here. And then it's allocating memory to do that. And then after the memory is allocated, it's going to append it to what's called an append-only file, AOF for short. Now, Redis has a lot of control here to do different things. We want to fsync that in a lot of different ways. Now, fsync can occur 3 different ways for Redis. And one way is optimal for this type of workload. You can fsync every periodical amount of time, so every several seconds, every second, something along those lines. And then basically that means that but anything that hasn't been fsynced is potentially not actually committed to disk. So that has some drawbacks. The other option is to use fsync on every write. So Redis keeps track of where the writes are. And in this case, you really want to make sure that if something is committed to this, that it's an action that is super dependent on other actions This would be really important to do this. So you want fsync on every write. So once you do that xadd, it's going to say, yes, I've committed it to the disk. And the third option is kind of more loosey-goosey, and that's just based on the operating system. So it may fsync a variable lots of time. But for this type of operation, you probably want fsync on every write. Now, in a success situation, it's going to return the stream ID back to your application. The key thing here is, though, if there is a failure that occurs in any of these steps, it will return an error. And notice that what's happening here is this is the last part of the actual information. So let's say there is a failure of the entire instance, you get a failure scenario that way. If there's a failure of the disk or the memory, you get a failure back to the client itself. So you'd know you'd have to do some sort of retry method. So that's really important in getting, making sure that when you're writing these things, that it is done in a very durable fashion. Now, looking at different things from how you might do this, of course, in a place where you have multiple instances. Of course, when you have very few actual architectures have just one instance of something, right? That's kind of the dream. You have multiple instances handling a load. So in this, for example, we have our order service here. Let's say we have 7 instances of it. You need to be able to manage this across an entire group. So just keeping track of that bookmark is not sufficient. You need to be able to keep track of that bookmark as a group. So what happens here is, this order 7 instance is reading this stream ID, right? And it takes some time to process this. At this point, there is a group that is maintained by Redis that is making sure that it's not giving these things out willy-nilly to multiple different instances, if that's your requirement. So in this case, what it's going to do is order 7 is going to be, doing whatever processing it needs to do, sending emails or doing some calculations, and to prevent duplicate work, it's going to do that and not pause the database in any way. But after it's completed, it will then acknowledge that it has finished with that. And we use the xact command, or the act just for short. So that's all fine and good, but that actually opens up another kind of hole, right? You want to be durable to any holes that are resistant to any holes that you might have. What happens, though, when you have a failure in that particular instance? So order 7 dies for whatever reason. In a on-prem environment, maybe that's something like you have some sort of disaster that occurs inside the data center, or maybe you need to do maintenance or something along those lines. You have to yank the plug sometimes. Now, in a public cloud, you have other scenarios that are even more unpredictable. You may have some sort of interconnectivity failure. You may have some maintenance windows. You need to be able to be resistant to almost any failure. Now, there's a particular pattern that you have to do when building this application to make sure you can do this. Now, in something like Kubernetes, what you would be using is a stateful set to keep track of the kind of names of the individual instances that are running. So in this case, when it dies and you bring it back up, it will know that it is order 7. And then what you do when you start up an instance is you just say, give me all of the things that I haven't processed yet. And 00 is the command arguments that you do here. But it's just important to know that that's there to make sure that you read back through anything that you would have missed. And this enables your any instance to go down at any given time and actually be able to make up anything that it has already reserved and not duplicate the work if you need it. Now, I've given similar presentations on this topic many times before, and some people gave me the feedback and walked away with an idea that I didn't necessarily want them to walk away with. Synchronous operations are certainly valid in a microservices architecture. So if you have, for example, order and fulfillment doing a synchronous operation over HTTP, there's lots of good reasons to do that. So let's give an example. So order sends some sort of REST request or a REST API request for fulfillment. Order is now waiting for a response. And it needs to wait for whatever type of rules that might be in place for a given piece. So it needs to get an okay from fulfillment. So in this case, it is having to do something else which is like, for example, update a status in a private database for order. You wouldn't want to do this in an asynchronous format. This would be possible, but very challenging to really master doing this in any reliable way. So that's certainly something that you'd want to do. So synchronous operations are still something that you have to do. But using asynchronous operations on a stream is also something that is valid. You really have to consider what would work best for your given circumstance. So for example, here, user is listening to order, so listening to a stream, right? Then order adds this new order to the stream entry, and then it sends an email out. In this case, you're not having that back and forth, right? Sending the email out is certainly something that you don't want to fail on, but it's also something that the order service doesn't need to wait around for anything to happen on. So certainly both will make up a more complete picture of your microservices architecture. Now, I do want to talk about another kind of component to this, which is the microservices architecture and latency. And this is really important in a hybrid environment, especially considering that latencies between services may be longer than they would be if everything is on-prem or everything is in a private cloud. So your overall latency really is the sum of the latency for all of the different services in a given operation. So if you have higher latencies, that becomes a problem very quickly. So let's take a look here. You have Fulfillment, and it does all of its database operations in 25 milliseconds. And you might think, hey, that's great. That is a very respectable figure for many databases. And you think, okay, I'm in good shape. However, things get worse when you have this across many different instances of a given, or many different services and many different instances, maybe even inside of this. So that actually becomes a very high figure. So just this 5 different operations that or 5 different components of the operation we're doing is 125 milliseconds. And that is probably intolerable for the overall user experience. So when you're looking at something, we like to talk about the instant experience in Redis, and that's anything less than 100 milliseconds is something you can't really understand as a human being. But here alone, just 5 different services in a row, doing something relatively fast becomes quite slow. So what do? You can still have your database access as 25 milliseconds, but putting a cache layer in is something that can really make a big difference. In this case, you have a cache layer that can respond in a single millisecond, and even though you're doing 5 of them, you still have a respectable 5 millisecond overall time. So that works out well. So not only can you really start thinking about how you might communicate as well, but the time in which it takes you to communicate is incredibly important, especially as you think about these arrows being a variable amount of time. Now, I do want to plug something here. My book that I wrote with my colleague, Loris Crow, this is Redis Microservices for Dummies. Much of this material that you saw today comes from this book. You can get the copy of the book for free in PDF format by going to the URL on the screen, bit.ly CTO-microservices to pick up your copy for free. Like I said, it's a quick read, less than 100 pages, and it goes over a lot of these things in much more detail than I could give on a 30-minute presentation. All right. Well, I want to thank you for the opportunity to talk about this, show you my book, and I'll be around for the Q&A session. So let me know if you have any questions. Thank you very much.